Hello everybody, and welcome to the first of 3 videos covering a subunit on complex functions while I'm out of town. So the first 2 videos will talk about complex functions. The next third video will talk about derivatives, and then we will save integration of complex functions till after I get back. That will be its own subunit. So this unit consists of complex functions and how do you take their derivatives. So we're now starting a unit, 2 subunits on the calculus of complex numbers now that we're done with essentially pre-calculus of complex numbers. So let's start with what a complex function is. Hopefully this definition will not surprise you. A function in general is simply something that takes inputs and gives you outputs. So a complex function is simply a function whose inputs are complex numbers and whose outputs are complex numbers. So here are several examples. So this first one says if I give you x plus yi, you give me back, the function gives back x squared plus y squared I. So kind of like a quadratic function, although not literally, you're not literally squaring this, but has the same flavor. So if you input 2 plus 3i, the function gives you back 4 plus 9i, for example. This next function literally is the quadratic, the squaring function. So if you feed in a plus bi, what you get back is a plus bi quantity squared. So here's a squared. This next term is bi squared. So bi quantity squared is b squared I squared. I squared becomes -1, and then plus 2abi. You could have a function that you feed in a complex number, and then what it gives you back is the real part, or maybe the imaginary part, whatever, of the complex number. So x plus yi, when it gets fed in, the output is x. So 5 minus 6i gets mapped to 5. For example, you could feed in a complex number, and then what comes back is the polar angle. Here you'd have to be a little careful. If you want a function, you would want to specify that the angle is between 0 and 2 pi. But anyway, so here I've spit out the angle between 0 and 2 pi for the number 1 plus I. So that's the idea of a complex function. In goes a complex number, out comes a complex number. Notice here, this 5, you might say, well, that's not really a complex number because there's no I term. But it is. It's a real number. So you could think of that as 5 plus 0i, if you like. So you don't have to have like an I term or a real term if you don't want to. You could output 7i or something. Okay, so here's just a handful of examples of complex functions. So a general observation is that any complex function, if you sort of manipulate it enough, can be written like this. There's like a real part and an imaginary part of the function itself. So if you feed in x plus yi, there's something in terms of x and y that's not attached to the I, and then something attached to the I. So here u of xy and v of xy, these are real valued functions. Because x and y here, x and y, these are real numbers. So here's an example. F of z equals 1 divided by z, the reciprocal function. So this, as written, does not look like real thing plus real thing I. So let's put it in that form. So if you feed in x plus yi, well, you reciprocate it, don't you, by definition? And then if you want to put it in this form here, basically I'm saying write this fraction in the form a plus bi, essentially. So if you want to do that with a fraction, you multiply by the complex conjugate. We've seen this plenty of times. So 1 times the conjugate is x minus yi. X plus yi times x minus yi is x squared plus y squared. And notice x squared plus y squared is a real number because x and y are real things. So y, x and y are both real. And so now you can just split that fraction into pieces and you get a u piece here, a real piece, and then imaginary piece here. So u is x over quantity x squared plus y squared, and v is negative y over, again, quantity x squared plus y squared. So any complex function can be written in this form if you want to write it in that form. Of course, this f of z equals 1 over z is much cleaner looking than all this stuff, but it's just a matter of perspective. Do you want it written in the form like a plus bi or not? It just depends on what you want. Okay, so here's an example. This is something for you to do, so you can pause the video if you want to and do this. So here's a function. You input a z, and what comes back is z squared plus iz. You feed in a complex number z, and what comes back at you is the conjugate of z divided by z. So if I were you, I would pause the video and see if you can do basically this kind of work to identify what the two functions are. And here are the answers if you want to check. Hopefully I made no mistakes here, but anyway, notice f, if you feed an x plus yi, here's your u of xy, stuff not attached to an I, and then here's your v of xy. And same thing for g, you feed an x plus yi, and if you trace through what happens with all this, you end up with this x squared minus y squared quantity over x squared plus y squared. Quantity is the u, and this other stuff is the v. Okay. So normally when you talk about functions, if you think back to Algebra 2 or something, you pretty quickly move to graphs, simply because graphs are a nice visual tool, lets you see what the function is doing. So if you have a complex function going, like any of these, right, f of x plus iy equals the square of that plus I times that, could we get a graph of this? Could we see what this function is doing? So where does the graph of something like a complex function live? So let me point out that you're feeding in complex numbers. Complex numbers are like a two-dimensional kind of deal. The complex plane is a two-dimensional place because you have a real axis and an imaginary axis. In other words, a plus bi is kind of just like the ordered pair ab. So your domain is two-dimensional, is all I'm saying. So you feed in things that come from a two-dimensional place. And then you're outputting complex numbers. So your output space is also two-dimensional. So inputs are two-dimensional, outputs are two-dimensional. And so this is just a general observation here that a graph of any kind of function, complex or not, lives in n-dimensional space where n is the sum of the dimensions of the domain and the range, basically. So the sum of the domain of inputs plus the domain of the, sorry, let me say it again. You take the number of dimensions of the domain, the number of dimensions of the outputs of the range, and add those together. So if you're inputting something from dimension 2 and outputting something from dimension 2, 2 plus 2 is 4. So complex function graphs live in four-dimensional space. So I'm not going to be drawing for you any graphs of complex functions. I can't give you a link to a complex function visualizer, for example. So there are ways to maybe kind of get around that we'll see in the next video, but you can't directly look at graphs of complex functions. So the last thing in this video just to point out is that most language around functions that you're familiar with will translate. So for example, a polynomial, what does that mean? It means the same thing it did, in 10th grade. It's just whole number powers on your variable with coefficients that come from the space you're living in this case, complex numbers. So in Algebra 2, a polynomial for you was defined like this, but instead of a z, there was an x. And an minus 1, and so on were real numbers. So now the AIs are complex numbers, but this is exactly what you would expect if you were to define a polynomial for the complexes. So other things like rational functions is the same deal. So a rational complex function is simply a ratio of complex polynomials, things like that. So the function language you use to translates. That doesn't necessarily mean that all your intuition about these functions translates also. We've already discussed how your intuition can break down pretty quickly when you move to complex stuff. But at the very least, a lot of the language translates. Okay, so that is the end of video 1 for the complex sort of derivative unit. So at the end of this video, I claim you can do a few things. First of all, you know what a complex function is. I claim if I give you a complex function in this form, you can write it as real plus imaginary thing. I claim you understand why we can't look at graphs of these, and that you understand that things like polynomial, language like that, translates. So in the next little video, we're going to talk about limits and continuity of these functions, concepts that you definitely need to talk about a derivative, which will be the third video.